Hello everybody. So today I've got with me Fredrik Nygaard, who readers of my website might know because of his series of articles about the capacitance model of gravity and the relationship between gravity and the electric universe. And Fredrik became interested in the research that Peter Woodhead had put together regarding the idea that the Earth may have a gas-filled centre, and Peter and I have talked about this at length in previous videos that are available on my website and on YouTube, and also I wrote this up into a couple of articles. And Fredrik contacted me a few days ago, and we're now speaking on the 27th of June 2017, because he'd very kindly written to me with a new article that had actually been posted on the Nature website about the Juno spacecraft mission. For those that are not familiar with Juno, it's a probe that NASA sent out a few years ago to go into orbit around Jupiter and look at the moons and things. And I've got this article in front of me, which is dated the 25th of May 2017, so now just about 5 weeks old. And I think Fredrik is a bit more clued in than I am. I did have a quick read through, but Fredrik's now going to go through why we think this article is significant and how it might tie into the earlier research. So thank you very much for spending some time with me, Fredrik.
Yeah, thank you. So yes, I read this article. I had to read it several times because what caught my eye initially was this reference to Jupiter's large and diffuse core. It's
right. I'll just say, just for people listening, this article is called "Jupiter's Secrets Revealed by NASA Probe." I should have said that earlier, but
yeah.
And a deep ammonia plume and a powerful magnetic field are among the many surprises uncovered by the Juno mission. And as it's on the Nature website. So sorry to interrupt you there, Fredrik.
Yeah, I jumped straight into it because it's okay. Towards the end of this article they start to talk about what they found when they were actually looking into the depth of Jupiter. They seem to have used some microwave equipment to bounce microwaves off of the atmosphere and to look straight into the center of this planet. I read this article and I came to the point where this mentioned a large and diffuse core. That's what they actually discovered, and this caught my attention because I'm still working on this gravity model and looking for clues, and this sounded like it was hollow. It's a strange way of saying that something is hollow, but then again, NASA would probably stay away from the word hollow if they discovered something unusually low density inside of a planet. So
that's right. So if we just dwell on that point for a minute, you'd think, we're often taught about the Earth that it's got this molten iron core, and therefore you think iron, it's a heavy element or relatively heavy compared to some of the others. And so you think of this dense core, and therefore you intuitively would think that Jupiter being a much bigger planet, that it would have a bigger solid core, wouldn't you? So
yes.
You'd think it'd be even more dense because it's got a more compressed on the core. So this, as you said, this phrase, a large and diffuse core, that is even more surprising to hear that coming out in this research.
Yes, certainly. And if you look up Jupiter on, in an encyclopedia or in a book about astronomy, you will see that everybody expects what you presented with is layers of matter, and it gets denser and denser towards the center. And then there's something very high density at the very core. And what they actually saw when they were looking into Jupiter was the opposite. They found something low density, and And then they even present some number in the article. Right. It sounds like it's tremendously massive. They talk about 7 to 25 Earth masses. And
yes.
And that sounds, that might be put in there just to throw the reader a little bit, because that sounds like it's tremendously massive core, even though they say it's large and diffuse. But then if you know that Jupiter is estimated to be 320 times Earth in its massiveness, then 25 isn't all that much. In fact, it's very small. And when you take into account the fact that they think it's very large core, maybe as much as half of the internals in the radius is this core, then it's very, very low density. It's much lower than it should be. Even a conservative estimate from the standard model would tell you that it should be 40 at least. And I think all the textbooks that you would open, they will speculate a much higher density than that. So the standard presentation that you will get from textbooks is that there's this atmosphere, and then there's increasing densities as you come closer to the core. The opposite is what they actually saw. And this takes everybody by surprise. But it doesn't, of course, take Peter Wood by surprise. Neither does it take me by surprise. This is exactly what we've been saying that is likely to be the case. So it's quite amazing that it's coming out in Nature like that. But they don't expand on it. They don't elaborate on it. They don't give you this extra information that this is actually a very low number, even though they use this euphemism about large and diffuse core. Mm.
Right, and then looking at the article, it's, I don't know whether I haven't studied it thoroughly, or maybe I should, but it's actually pretty short, isn't it? I could do a quick word count here, but I think it's only something like 500, probably less than 500 words. I'm just going to try and do a quick word count on the word processor just to see how it. And I don't know, does it link to another paper? There are some references at the end to several.
Yeah, there are several references.
Yeah, but I haven't had a chance to see if, what it actually uses from those papers, whether this is just some, so let's just see how many words it is. I've just pasted it into there. But 625 words I've got here, so it's a pretty short article. And like you say, it's like they're being cagey about the details.
Yes.
But you mentioned just before we started recording about, considering the radius of a sphere and the volume, because you've got a cubic term. So I don't know if you want to go through that again in relation to this.
Yes, because of the cubic term, then if you have something that is half the radius of a sphere, then to find its total volume, the volume of the core, it's actually 1/8.
Right.
And the thing is that if you look this up on NASA's own fact sheet, you will see that the total mass of Jupiter is estimated to be 320 times Earth. Now, if you do a simple division, 320 divided by 8 is 40. That's where this number 40 comes from. Yet their own measurements, when they actually measure the density, and there's an estimate from that in this article, they say it is 7 to 25 times Earth mass. So it's much smaller, or much less than the 40 that should have been the minimum from using their own sort of estimate or predictions, right? So this is completely contrary to their predictions about how Jupiter would actually look like when you look into it.
So in other words, this is a sort of large and diffuse bit, isn't it? That they're essentially saying that the core isn't as, aren't as many masses inside the core, Earth masses as it were, as they were expecting.
Yes.
So, and it says, I'm just reading a line from the article, the core could be both larger and more diffuse than expected, extending out to as much as half of Jupiter's 70,000 kilometre radius. So if the core is extending outwards, it's not really a core, is it?
No, it isn't. And it's actually very reminiscent of the Drew, or together with Peter Woodhead, because I remember looking at your pictures from that first video that is very well made and some very good illustrations. I was struck by the fact that the shell is actually fairly thin, all in all, compared to the overall size. You were doing this analysis on our own planet, and you end up with a fairly thin crust, right? Now, what we're seeing with Jupiter is Jupiter's only atmosphere, right? It's only gas. So you get the same shell, but then in gas form, and you end up with this then, according to the estimates or the predictions of this capacitor model that I've developed, the highest density should be halfway, roughly, inside this shell, and so should the highest density of Earth's shell be, right? But our shell is in solid form, while Jupiter has a gaseous shell. Still, this goes a long way in confirming the predictions of this model that I developed based on Peter Woodhead's work. So this is very encouraging, very much so.
Yes, indeed. And as he was also saying earlier on, just before we started recording, that we've got this article in Nature, but doesn't seem to have been widely sort of distributed, does it, or widely talked about?
No,
it's not,
and that's quite understandable, really, because this is if it really is true what they're saying here, then this is really radical stuff. It could toss everything into disarray when it comes to the standard interpretation of things. We assume this high density core in all planets, and now we know that this is not the case for Jupiter. If it's not the case for Jupiter, it's hardly likely to be the case for any other planet, or even the Sun. Mm. The Sun might not even have a very dense core. Well, the whole model that we have, the official model, the one that you, again, in textbooks read about, must have a high density core, because you won't be able to get this fusion. There can be no fusion at very high pressures and high densities. But if there's no high density inside of our Sun, there's no fusion going on there. So that there goes the whole model of the conventional model of the Sun. It just doesn't add up.
Right, and I mean, of course, some people I've read in the past in one or two astronomy books, they've said something along the lines of, well, if Jupiter was like 30% bigger or something, it'd be a protostar.
Yes.
Because there'd be enough, density at the core, according to the standard, as you say, to the standard model, that fusion would begin, or a kind of fusion, and you'd get, it would become a star in its own right. Yeah. And I think even in the 2010 film, the Arthur, based on the Arthur C. Clarke story, I think that's the plot line, isn't it? That Jupiter becomes a second star because somehow fusion starts in it. I forget the exact.
Yes. And the irony here is, of course, that that's very unlikely to be the case. Yet, I think the assumption that Jupiter could turn into a star, if it were to grow, is not wrong. We know that all stars have to have a minimum size. So that part of the story is correct. It's the assumption that fusion is the driving engine of stars that is incorrect.
Yes.
So while I would not, in fact, I'm a big believer in the fact that if Jupiter was to grow significantly larger, it would become a brown dwarf. Was it getting even larger, it would be a white star like our own, and etc., etc. So the size of an object gives an indication of how hot it is, but that heat isn't generated by fusion. It's generated in a very different way. So
right, and so the other things that we'd sort of had on the list to sort of mention was Jan Lamprecht, who Peter and I talked about.
Yes.
Because although it isn't directly relevant to the Jupiter story, because they haven't done seismic surveys of Jupiter, but nevertheless, it was he that concluded from seismic studies of the Earth and the way that these signals are refracted that this could be interpreted as having he said a hollow core. But Peter and I revised that slightly to say a gas-filled core.
Yes.
So I don't know if you had any other thoughts on that you wanted to bring at this point.
The thing is, what is interesting here is that Jan Lamprecht uses seismic data from Earth, and he by using a hollow Earth model in which densities don't really increase all that much, and it's actually hollow, so it's actually at some point. Then he actually shows that this would work quite well with the data that we have. In fact, it would be an easier way of explaining seismic data than the current solid core model. Yes. But the fact that he does this he comes in from one angle, right, which is the seismic data angle, and he comes to the conclusion, well, Earth must be hollow or is likely to be hollow. Then from a completely different angle, NASA now has this Juno probe probing Jupiter. And what do they find? Exactly the same. So there's two different angles of interpretation, two different types of physics used. There's two different, and yet you end up with two very similar conclusions, right? They both conclude that these planets are hollow. And I think that's interesting because the more different angles you get using different kind of physics, different kind of data, and where you end up with the same conclusion, that's starting to add up to a story, right? Because if you just go through the same data over and over and over again and lots of different people, that's not so interesting. But when we have two completely independent data sets and they both come to the same conclusion that, well, looks like it's hollow, then the case is strengthened quite a lot, right? And the more you get of that,
you've got to take that conclusion, the possible conclusion, more seriously.
Yes, much more. Yeah. So now there are two independent ways of analysis that both end up in planets, the conclusion that planets are hollow. So that's very interesting. And when it comes from NASA, you start to think, well, boy, even they are coming to that conclusion. That's interesting.
It is, isn't it? And I think I had a thought while you were speaking there, and obviously people can go onto the website and read about your capacitance model, which is how you kind of got into this. And you started looking at the problem with gravity. Yes. And I really enjoyed reading your articles on this. And we talked, I think, before about how the articles that you'd done were kind of a thought exercise, and you've developed the thoughts and conclusions through these articles. I mean, I've left them all on the website, but the later ones that you've done, you feel are more refined and more, perhaps more accurate. So there's that. And what I thought while we were talking was, it's been known for a long time that Jupiter has a lot of electrical activity, doesn't it? Because I think it was back in the Second World War, they were picking up these mysterious crackles on their radios, and there wasn't any obvious effect from the Earth. And I think it was eventually worked out that what these radio receivers were picking up were discharges from thunderstorms on Jupiter. Now, I'm sure you could find this if you go and look at the appropriate pages. And I was therefore thinking that if you've got this larger object, and this capacitance model is correct, and the EU model is also correct, then if you've got a larger object, you're going to have more charge, and therefore you can have a bigger range of electrical effects. I'm taking a fairly simplistic view in this way, but I don't know what your thoughts would be on that.
Yeah, I agree completely. The capacitor model that I came up with, I call it the model on purpose because it's not really a theory. It doesn't really say anything in detail how gravity works, but it does say a couple of things. It basically says two things. First of all, it assumes that gravity is charge pulling matter, not matter pulling matter, right? So that's a separation from Newton. And then it also says that there's this there's actually two effects coming into play. There's a dipole, since charge is a dipole thing.
Yeah.
You have a dipole effect, which has there's a repelling element to gravity. That's only short range, by the way. There's a short range repelling effect between large objects. It doesn't affect smaller objects, but large objects will have a repelling effect, including the internals of all large objects. They will repel itself, right? So that will ensure a cavity inside all large objects. So, but basically the more charged an object is, the more gravity it will have. And you're right also, the larger it is, obviously, the more charge it can actually hold. And Jupiter can hold an enormous amount of charge. Is therefore also has this very high gravity. But that's also a function of mass, of course. There's matter there.
Yes.
And that's why it's so easy to confuse the two, and why we have assumed for so long that it's mass that does this, that it's mass attracting mass, while it's actually charge that attracts mass. That's the only separation in the model, and then I show that you end up with basically the same equations as Newton, but you get this effect with the hollow inside. There's a repelling effect that would only come into play if two large objects came close to each other. And for the rest, it's exactly the same as Newton's equations. So there's a small difference, but not a very big one. And of course, the truly measurable thing is this prediction about the hollow, and also the prediction that the area of largest density would be halfway into the shell somewhere, right? That the highest density is not located towards the center of a planet. It's located close to the surface, in fact. Fairly close to the surface.
And that, I think, goes, sort of ties up a bit in some sort of way with what Peter and I were trying to address with the center of gravity problem.
Yes.
I mean, that's one of the things you've got on the list here.
Yes.
I know it's not quite the same thing you said there, but there appears to be some kind of relationship there to where this density, ends up because of the charge separation and so forth.
Yes, that's right. I started working with Peter Woodhead because first of all, I was very much attracted to his overall theory that it had to be a hollow, that there's no mysterious generation of matter inside planets. The idea that matter just somehow is generated inside of planets it didn't rub well with me. So
Right.
So I was very much attracted to Peter Woodhead's story. But of course there was this problem with center of gravity, and you got criticized about this from several angles, I'm sure. That's what my impression anyway was, with talking with Peter Woodhead and working with him. And then I decided to, well, I'm not going to let this stop me from finding an explanation. So I started this journey then, where I was trying to find ways of explaining this increased gravity in a slightly different way. But yes, so there's a center of gravity idea that it moves out, that with that was presented in the very first video that you made. That's actually incorrect. That's not exactly how it works, but it's very, if you just visualize it, it will actually give that effect. So
it has that appearance.
It has that appearance, but it's actually caused by something different. And the key to understanding this is that, well, a body that expands like that is actually becoming more charged, and not just a little bit more charged, but a lot more charged. And this explains.
We can easily make the argument that, we've got the solar wind constantly impacting on the Earth, and that in some way could, contribute, or it could be entirely the contribution of the additional charge, couldn't it?
Yeah, it does. But for that story to add up, you can't just add charge to a body that can't accept it, right? A body has to be able to accept more charge. So we constantly bombarded, and my thinking is that our planet is always fully charged. So it has always been fully charged. The thing is that once it starts to expanding, and it's expanded as a shell, you get that Earth is actually a capacitor. And a shell, an expanding shell, is a very efficient capacitor. So it actually is able to draw much more charge to itself. And we're talking about an exponential amount, not a linear. So, and this makes it even easier to explain the dinosaurs, because the dinosaurs, even if gravity if gravity is only twice as much as back by the time of the dinosaurs would still have a problem. But if it's more than that, if gravity back in the time of the dinosaurs was more like what it is on Mars today, then the problem with gravity actually disappears. And the interesting thing is that the size of Earth back at the time of the dinosaurs is in fact the same size as Mars, right? Yes. And that's very interesting because Mars, although it's half the size of Earth, doesn't have half the gravity, which is what would have been expected from a standard interpretation. It has only 1/3 the gravity. It's only 1/3.
I suppose they would assume the density was different.
That's what they're saying, and that's why they assume that there is a super dense core in our planet. Yes. That's because there's no other way of explaining Mars and Earth, the difference between it. But if it's not really mass, but just charge, then suddenly that problem also disappears. Earth doesn't have to be much more dense than Mars. This whole story that Mars is less dense than Earth doesn't make very much sense, because the Earth is, by just looking at it, is full of water. But that's of course only on the surface. But there's also a lot of rock, no ordinary gray rock. Mars is a red planet. It's full of iron. The surface of Mars is much denser than the surface of Earth. So why would a planet that is denser on the surface be somehow less dense in the center? It sort of doesn't really add up much.
It doesn't, does it? Now you mention it.
So, but if you take the capacitor model and assume that Mars hasn't really expanded much, it doesn't look like it has expanded much. So we can just say that it's probably very similar to infant Earth, but without the atmosphere and the good climate and everything, of course. But then just size-wise, it has.
And just diverting onto that for a moment, I remember reading years ago that it was, it said there's no plate tectonics on Mars, so that would then, if we make our argument that the plate tectonics, as it is called, I mean, James Maxwell calls it expansion tectonics, as evidence of the expansion, then for some reason, then, Mars hasn't undergone the same processes, although, of course, what's his name? Neil Adams disagrees with us because he's made these videos where Mars has expanded.
But not by that much. Even Neil Adams agrees that Mars has only expanded a little. There's this, Valley Marineris, I think it's the name of it.
Valley Marineris.
That's the only visible crack on the surface. There's no other cracks. There's some volcanoes, but apart from that, there's very little activity. But Earth is full of cracks everywhere, and there's volcanoes everywhere, and it's expanding, clearly expanding.
And the other thing, we've got a couple more things on the list. The one thing which I did want to just mention here, which I saw on your list here today, and it's really interesting because you'd mentioned the Biefeld-Brown effect and Thomas Townsend Brown. And of course, this is all, and I don't know why I didn't cotton onto this earlier, because I started writing about something about this when I found out about it, back in 2004. And of course, it was that they were doing these experiments with X-ray tubes, I think, and they use obviously a very high voltage, and therefore they've got an associated charge and probably capacitance. And they noticed these had anomalous movements, sort of beyond what they should be doing. And that's how Thomas Townsend Brown came to do experiments with his, I think it's called the gravitator disk. And that's latterly been developed into these lifter models. And, I think you'd mentioned here that you wanted to just mention about the capacitor model being in relationship to that and the iron wind and so forth. So talk about that.
Yes. The thing with, the capacitor model that I sort of concluded with, as far as gravity is concerned, is that it's actually in accordance to what, Thomas Brown, stipulated in his time. And that is that if you charge a capacitor sufficiently, there will be a lifting effect. Provided you face the negative pole down and the positive pole up. It's very important. If you do the opposite, you get much more gravity. And this is this ties up to in my model, there's two things, there's a short range effect, which has this ability to repel. So there's in my model, there would be a short range anti-gravity possibility. You could engineer, a flying device, that could take advantage of that close to a planet, but not at a large distance. Then the effect disappears, because I'm assuming that the repelling effect is it tapers off with the inverse cube law. So it's actually, it disappears at a large distance, but it can be exploited on a shorter distance. So,
right. And also you'd mentioned on the list, because I know that I posted another article on this from you not too long ago about the Morton-Spears capacitor theory. So, just talk about that for a couple of minutes or so.
Yeah, I came across this, his papers and his work, actually after I stipulated my model. And there's this, Morton Spears, who actually did some practical real life lab experiments, related to, capacitor capacitance and gravity. And he came to the same conclusion as Thomas Brown. And Morton Spear's theory is a proper theory. It actually says something about exactly how the mechanism, this mechanism works. What's kind of ironic about it is that he spends some time towards the end of his second book. He wrote 2 books. In his second book, he's spending quite a lot of time trying to explain how this nevertheless doesn't mean that Earth is hollow. Obviously, he thought that was a little painful conclusion that he came to himself. And so he sort of messes up his own work a little, because he had a fantastic opportunity there to be the first, because he wrote this in 1996, I believe. So he would have been the first one to come with a theory suggesting a hollow planet, right? But he spent, instead of coming to that conclusion, he spent some time arguing why his theory would nevertheless not produce this effect. It makes no sense. But,
okay. Now, I think just for listeners, because I seem to remember you mentioning that there was two people involved with this capacitor theory that you just described, and one person actually wrote up a simplified version.
Yes.
Is that? Do I remember?
Yes,
that
that's true. The simplified version is how. Well, I just like everybody else, I prefer to get the quick and easy story first, and then progress to the more heavy stuff afterwards. If I find the quick and easy story convincing. So there is a short write-up, very easy to read. I can't remember his exact name though, but I think if you Google this, you'll find that there's a short version.
I think you did mention this in the article, so people can go back and read the article.
Yes. I linked to this easier paper. Yeah, absolutely, I did. That's true. In the articles, there are links. Mm.
And then, so there was a couple of other things then just on the list. And then we'd start to talk a bit about this earlier on in our talk today. But how, if you take these conclusions in that, we're looking at, going back to the NASA article again, Jupiter has a large and diffuse core. That means, we can therefore speculate with some justification that stars have a quote unquote large and diffuse core. So what does that mean in terms of things like neutron stars and black holes, for example? Just talk about that.
That's another interesting conclusion, is that this black holes and neutron stars that are believed to exist. Although I'm not going to pretend I've looked into the detailed maths of this, but we're talking about purely logical terms. It's thought to exist because when you have a so-called gravitational collapse, where a star falls in on itself. This is pure nonsense, by the way, but this is what people truly believe out there, and this is the official story. So the official story is that you can have something called a gravitational collapse. A star falls in on itself. Then obviously it has to fall in towards the center of itself in order to collapse properly. And if it's big enough, the idea is that it will produce a neutron star. But if it's even bigger than that, it can produce a black hole. This whole story is predicated on the idea that everything falls in towards the center. That's the place that things fall. But if that's so, then why wouldn't Jupiter already have all its mass located, or most of it, in the center, right? Because it's just a gas planet, so the heavy stuff should just fall in towards the center. But no, it has, quote unquote, collapsed into a sphere. That's what has happened, right? So if there's any further collapse, it will just make the sphere somewhat harder, maybe into a liquid first and then into a solid, but it wouldn't actually collapse toward the point. Because logically speaking, if gravity works the way we are observing it through NASA's, with this space probe, then there is a highest density point quite far away from the center. That's the place that a further collapse would also go to. There's no reason to believe that the initial collapse is towards a sphere and then suddenly gravity decides to do it differently later, right? So the whole model that is required for neutron stars and black holes to exist just falls apart. It doesn't make any sense.
It does, doesn't it?
And it doesn't make much sense even today. I mean, I was always very skeptical to this idea that there is such a thing as superdense matter. And certainly black holes, it's just wild nonsense. But now we have observations that sort of seem to indicate that is indeed nonsense. That's not how gravity works. It does not pull things in towards the center. It pulls things towards a shell.
Yes, and if I may just throw something into the sort of discussion here, and that I'm thinking about, when I read a few astronomy books when I was at university and stuff, Math University, and they tell you about as you say, the neutron star and certain conditions. I think it was 2.5 solar masses or something, and if you had a star that was bigger than that, it would collapse to a black hole or something. And but then they talked about obviously supernovas being the result of this, and that at some point, I know not when, but you get this collapse, and then there's a reaction against that, which causes a star to explode and form a supernova.
Yes.
Which kind of, like you said a minute ago, when you start to really think about that, particularly based on this latest Jupiter article, it does become very much more shaky. And also, then I think, well, maybe there's another explanation, because supernovas, as they're called, have been observed. We had the one in the Large Magellanic Cloud in 1986, which is still being observed today, as I'm sure you're aware. Yes. So we could then just for a minute think, well, maybe that's the result of an overcharge, so that you've got a star building up a lot of charge, and at some point there's some type of reaction which is to do with an overload of charge or a discharge of some kind, which causes this incredible explosive effect. We just don't know, do we?
No, we don't. But there is if you probably haven't heard of this, that there is this. We are going to talk about the electric universe model to a sort of a conclusion that this leads up to this, because the electric universe community has a very appealing explanation for supernovas. Good. There's his name is Donald Scott, and he so on YouTube you will find a lecture by him on the formation of galaxies and stars. So I think if you just search Donald Scott,
I'll do that.
Formation of, you should look at that. That's very, very interesting stuff. And it's observation now that we have Hubble telescope. Observation indicate that it's an electrical event. It's not the death of a star, but actually the birth of a star and a solar system even, maybe. So what we're looking at is not the end of a life of a star, but the start of it. And very many things are actually turned inside out and upside down with this this new paradigm. So many things that we have assumed, like the highest density is in the center. No, it's out towards the perimeter of an object. Right? The supernova is not the death of a star; it's the birth of a star. And the list goes on. Actually, there's quite a few things that will be completely different interpreted under an electrical model. So that's really worth looking into. You should have a look at that.
I'll definitely do that.
Very good stuff.
Okay, great. Yes, I wasn't aware of that. I perhaps, spoke slightly out of turn because I haven't.
Yeah, but you were thinking correctly there. It is in the end a discharge that we're actually seeing. The great flash that's obviously there because we can see it is not a kinetic explosion. It's an electrical discharge, enormous one. It's the size of a solar system, so it does brighten up the area quite a lot.
And also you'd mentioned in an earlier message that we'd exchanged that obviously I think Peter had some more thoughts that he wanted to talk about, so I'll probably get him and do a similar thing with him, I think, maybe over the next few weeks if he feels that he wants to do that. And I'll post that as well. So
I think I noticed that this first video that people keep talking about it and keep coming with it. I think you definitely should talk about that and also say a little bit about the progress that he has made too, and what he thinks now is this whole center of gravity problem that you stumbled into, and take that needs. I feel that needs a sort of a conclusion, because I see a lot of people referencing Peter Woodhead, but there's always this. You never really got to the final. You didn't round it off, sort of. I missed that. So
okay, now is that the first video we did that they're referring to? Do they refer to the second one? Because I haven't really looked at the forum posts at all.
It's the first one that has most where people refer to it. I don't. Yeah, I do see links every now and again. People linking to it, and it's always the first one. Yeah. But still, the second one is a very good video too. I think a third one where you maybe so to talk a little bit about gravity. And there's so many theories out there, and many of them many of them fit this model that I came up with. The key to understanding, I'm calling it a model for a reason. That's because I don't say the exact workings, but there's a whole set of theories that assumes charge to be the cause, right? And there's another set of theories that assumes mass to be the cause of gravity. And then this is that's the conventional thinking, right? That's Newton and that's Einstein. Those are the two big ones, right? But the charge alternative is rarely talked much about, and that's why people don't really realize it's there. And I think I did a pretty good job of just summarizing the overall effect that can be expected from a charge-based model. Yeah. That's
okay. All right then, Fredrik. Well, I'll try and get together with Peter and update that, but obviously it's a bit difficult to, sometimes people don't pick up on the updated material, so, we kind of might be stuck with that for a while until maybe somebody else produces a new video including all that information together in one thing, that's updated with everything perhaps, I don't know. So we'll see how that goes, and, obviously I'll talk to Peter and we'll try and produce something, either just an audio or a video as well,
That would be very nice. Yeah, I hope you do. Okay. Yes. Thanks for having me on.
Well, thank you very much again, and we'll talk again soon.